Welcome. In this lecture, we will discuss step response of feedback amplifiers. Our objectives for this lecture are the following. Describe how feedback changes the step response from open loop to closed loop. Describe the step response at different phase margins. Infer the phase margin from the closed loop step response in the time domain and the closed loop gain response in the frequency domain. And lastly, identify a good phase margin values for a feedback amplifier with good speed and acceptable ringing or peaking. It was mentioned in a previous lecture that a system is stable if all poles of the system are at the left half plane of the S-plane or the complex frequency plane. If at least one pole is at the right half plane, then the system is unstable. Another way to determine stability is through the phase and gain margins. A positive phase margin or positive gain margin means that the system is stable. A pole along the left half of the real axis contributes a time-decaying term that is stable or does not lead to instability. Meanwhile, a complex conjugate pole on the left half plane will contribute time-decaying terms with some oscillation. However, these terms are also considered stable or do not lead to instability. However, the design of our electronic systems goes beyond ensuring stability. We also need to evaluate if the oscillation is taking too long to decay or if the ringing or oscillation is too large. As a rule of thumb, to ensure stability, we can design our system to have a minimum phase margin of 45 degrees. This gives the system some margin to account for variations and degradation of the circuit or its components. The operating temperature may also cause the transistors or passive components to change behavior, move the poles, and cause instability. We want our system to remain stable despite changes in temperature as well. However, since this is only a minimum, what then is a good target? Do we really want a maximum phase margin of say 180 degrees? Is 90 degrees enough? Or is some other value better? As we will see in the next slides, there are also disadvantages with very large phase margins. To help us assess the impact of phase margin on our system, we will consider a closed-loop system's response to a step input or its step response. We will limit our analysis to an amplifier with two open-loop poles and a purely resistive feedback factor. Aside from simplifying the analysis, we have also pointed out previously that the first two poles are most critical to the stability of the system. The conclusions that follow should therefore approximately hold for systems with more poles as long as the third and latter poles have little effect on stability. The same concepts must be reviewed or verified if the third pole or some other zero is affecting the phase margin of the system. Proceeding with the step response analysis of a two-pole system, we will define first our variable. Again, A of S is used to denote the open loop gain, the gain from the error signal, which is the gain from the error signal to the output signal. A of S has a low frequency gain of A0 and two poles P1 and P2. Note that the poles actually lie in negative P1 and negative P2 in the S-plane based on how we have written the equations. Since we are assuming a real positive feedback factor, then we expect that the closed loop response will still have two poles. This time we are using P1CL and P2CL to differentiate the pole locations from the open to closed loop. Also, the DC closed loop gain is given by A0 over 1 plus T0. In the Laplace or S domain, the output can be described by simply multiplying the LTI system's impulse response to the input. Since we are considering a step input, then its form in the S domain is some V step over S, where V step is the magnitude of the step in the time domain. For our two-pole closed-loop system, the output response in the S domain will be ACL0 times V step times 1 over S times 1 plus S over P1CL times 1 plus S over P2CL. Note that we now have a third-degree denominator with the inclusion of the step input. We then have to do partial fraction expansion before doing the inverse Laplace transform to get the time domain response of the closed loop system to a step input. If the closed loop poles still lie within the sigma axis or are purely real in the left half plane, then the step response can be shown to follow the written form after partial fraction expansion. Note there is a slight change in notation from P1CL and P2CL to omega P1 and omega P2. Thus, it must be remembered that omega P1 and omega P2 pertain to the poles at closed loop. The inverse Laplace transform of the expression above is the time domain step response, although the u of t factor is not explicitly shown. We know that the step input contributes to a non-zero final value, while the two real left half plane poles contribute exponentially decaying terms. On the other hand, if the closed loop poles are complex conjugate at some negative rho plus minus j mu in the S-plane, then the partial fraction expansion will be of the form shown. The inverse Laplace transform of the expression or the time domain step response is then composed of a non-zero final value from the 1 over s term and an exponentially decaying sinusoidal term. We will focus first on the first case where the poles are real and the step response has two exponentially decaying terms based on omega p1 and omega p2. Let's take a step back first and look at an open loop amplifier's step response before that of a closed loop amplifier. Note that if the open loop amplifier has two poles, then the general form of the transfer function will be the same as that of a closed loop response, and thus the time domain step response will still follow the form shown. From the equation, we can say that the larger omega p1 and omega p2 are, the quicker their corresponding terms decay in time. Thus, the actual pole locations determine how long or how short the decay will be. The major difference between the step response of an open loop and a closed loop amplifier, aside from the magnitude of the gain, is the difference in the pole locations. Open loop amplifiers, for example, or op-amps, are normally designed to have a dominant first pole. That is, omega p1 is much less than omega p2, omega p3, and so on. Thus, for open loop amplifiers, the last term in the step response expression will be negligible due to two reasons. One, omega p2 is relatively large, that it decays quickly, and two, the factor k2 itself is much smaller relative to k1. Thus, the characteristic step response will be dependent mostly on the frequency location of the dominant first pole. Shown here are normalized plots for the different pole frequencies. Note, for different dominant pole frequencies, note that in all three cases, the term related to the second pole is negligible. As can be seen from the plot, the larger omega p1 is, the faster the decay, and the faster the output reaches its final value. Note that with our assumptions, f1 will be the bandwidth of the amplifier. Thus, the larger the bandwidth, the faster the response. However, we know that the poles will move from open loop to closed loop depending on the amount of feedback. This means that the step response of an amplifier will also change depending on the loop gain. One thing we might expect, though, is that at closed loop we are trading off gain for bandwidth. Thus, at closed loop we expect that the rise of the output will be much less than 1 millisecond or much faster than compared at open loop. However, if at closed loop the first pole is not anymore dominant, then the described approximations where the second term is negligible may not anymore hold. We have already described previously the root locus or the movement of the poles in a two-pole system. We have also noted that all the three cases shown are stable since the poles are on the left half plane. However, one thing we do not know yet is how the phase margin changes as the closed loop poles move. To help us analyze the system in a more systematic fashion, we will describe the three cases as overdamped, critically damped, and underdamped. In the overdamped case, the poles are real and apart. Thus, one of the poles is slower and limits the speed of the response. There is also no ringing or oscillation as the poles are still real. In the critically damped case, the poles are overlapping in the real axis. Thus, no one pole is limiting the speed, and the fastest response without ringing is achieved. There is no ringing since the poles, again, are still real. Lastly, in the underdamped case, the poles are complex conjugates. The response is still considered fast as long as the poles are not too far from the real axis. However, the response has some ringing with a frequency based on the imaginary part of the poles. One question we will answer in this lecture is, how are the three cases related to the phase margin of a two-pole system? Let's revisit first the phase margin of a two-pole system. By definition, the phase margin is simply the phase of the loop gain at its unity gain frequency minus negative 180 degrees or plus 180 degrees. Since we are assuming a real feedback factor f, then the loop gain will have two poles which are the exact same poles of the open loop gain. The first term can then be expanded to the angle of T0 or simply 0 minus the tangent inverse of omega u over omega p1 minus the tangent inverse of omega u over omega p2. However, if omega p1 occurs much earlier than the unity gain frequency of the loop gain or omega u, then we expect that omega u is greater than 10 times omega p1, and by the unity gain frequency omega u, we expect that the first pole should have already contributed a phase shift of negative 90 degrees, which is also shown in the figure. Thus, the phase margin is approximately equal to 0 degrees for the phase of T0 minus 90 degrees for the contribution of the first pole minus tangent inverse of omega u over omega p2 plus 180 degrees. Simplifying the equation, we get that for a two-pole system with a dominant open loop pole, we will have a phase margin of 90 degrees minus the tangent inverse of omega u over omega p2. This expression should approximately hold for a loop gain T of s with more poles and or zeros as long as they occur at frequencies much larger than omega u. This formula or expression tells us that the phase margin is dependent on the relative position of the second pole to the unity gain frequency omega u. Ideally, the second pole should appear after the unity gain frequency to get a decent amount of phase margin. In this case, omega u over omega p2 fraction is less than 1 since omega p2 is larger than omega u. Thus, the tangent term is less than 45 degrees and we get a phase margin between 90 degrees down to 45 degrees. However, if the second pole occurs earlier as shown in the red lines, then the phase margin will be smaller. In this case, the omega u over omega p2 fraction will be more than 1, and the phase margin will be between 45 degrees to 0 degrees, which does not meet our rule of thumb presented earlier where the phase margin should be at least 45 degrees. The previous equation was based on the ratio of omega u and omega p2, which are the unity gain and second pole frequencies of the loop gain. Now we will go back to the closed loop response and try to relate the phase margin to the system being underdamped, critically damped, or overdamped at closed loop. We start with the general closed loop expression based on the frequency-dependent A of s and a purely real f, which leads to a frequency-dependent T of s. We will use D of s to denote the denominator of the loop gain, which should contain two factors of our two-pole system in consideration. Multiplying both numerator and denominator by d of s, we get that the closed loop gain ACL of s is 1 over f times t naught over d of s plus t naught. To determine the roots of the denominator, we need to expand d of s. So d of s here is expanded plus t naught. We also multiply both the numerator and denominator by omega p1 times omega p2 to make the s term in the denominator have a factor of 1. Distributing omega p1 and times omega p2, the numerator becomes a naught omega p1 omega p2. Since t naught over f is simply a naught, while the denominator becomes s squared plus s times omega p1 plus omega p2 plus 1 times t naught times omega p1 omega p2. We can now identify the roots or the pole locations of the closed loop response using the quadratic formula. The poles are found to be at negative omega p1 plus omega p2 over 2 plus minus square root of omega p1 plus omega p2 squared minus 4 omega p1 omega p2 times 1 plus t naught all over 2. We repeat here the result for ease of reference. For unique roots or an overdamped system, the discriminant must be positive. Thus, omega p1 plus omega p2 squared must be greater than 4 times omega p1 times omega p2 times 1 plus t naught. However, we can approximate that omega p2 will be designed to be much larger than omega p1 and that t naught is much larger than 1. Thus, the left-hand side is approximately omega p2 squared only, while the 1 plus t naught factor on the right side is approximately t naught. Cancelling omega p2 on both sides, we get that omega p2 must be greater than 4 times omega p1 times t naught, or 4 times the gain bandwidth of the loop gain. For overlapping roots or a critically damped system, we just replace the inequality with an equal sign, but since we made some assumptions and approximations along the way, then omega p2 is approximately equal to 4 times the gain bandwidth product of the loop gain. It must be remembered that omega p1 and omega p2 are the poles of the loop gain, which came from and must be the exact poles of the open loop gain when dealing with a purely real f. Thus, omega p1 and omega p2 in the formula shown are not the poles at closed loop. Again, we rewrite the result from the previous slide where the second pole of the loop gain is 4 times larger than its gain bandwidth product for a critically damped response. And since omega p2 is larger than the gain bandwidth product of the loop gain, then the loop gain must exhibit a single pole-like response beyond omega u. This is shown in the figure. Note that the plot is the loop gain and not the open loop gain nor the closed loop gain. For such a response, the unity gain frequency is approximately equal to the gain bandwidth product. Thus, for a critically damped system, the second pole is approximately equal to 4 times the unity gain frequency of the loop gain as well. And we can also write this as omega u over omega p2 is approximately equal to 1/4 and use this to determine the phase margin of a critically damped two-pole system. Evaluating the expression reveals that for a critically damped system, the phase margin is approximately 75.96 degrees. The situation can be visualized in terms of the frequency response shown. The second pole of the loop gain is 4 times the unity gain frequency, and the phase margin, as measured at omega u, is around 75.96 degrees. We can then identify that for an overdamped system, we will have a phase margin of greater than 75.96 degrees, while an underdamped system, the one with complex conjugate poles, will have a lower phase margin of less than 75.96 degrees. Knowing how the phase margin is related to the damping of the system gives us an idea of what the step response will look like and vice versa. Plots of the step response of a closed-loop system with different phase margins is shown. The black dashed line is the critically damped case, where the decay is fastest when there is no ringing or oscillation. As the phase margin is decreased, the system becomes underdamped. The smaller the phase margin, the slower the decay of the oscillation becomes, since a smaller phase margin means that the system is closer to becoming unstable. We can also see that there is a larger overshoot beyond the normalized target of 1 volt for phase margins smaller than 75.9 degrees. However, note that it is actually the 60-degree phase margin case that was the first to reach the 1 volt final value, although with some ringing and oscillation. Thus, if a fast response is needed, then a good target for the phase margin will be somewhere between 60 degrees to 75.9 degrees. Beyond this, a smaller or larger phase margin will result in a response that is slower. Additionally, if a smaller phase margin is used, the ringing becomes larger. Finally, note that the response is much faster than the open loop case, since the bandwidth at closed loop is much larger. The x-axis is now in nanosecond scale as compared to the open loop case, wherein the scale is in the milliseconds. Of course, the actual speed will still depend on the actual poles of the system, and the transient of the closed loop may be faster or slower than the one shown in the figure. To help us visualize what happens in the frequency response, let us inspect the normalized magnitude response plot for a two-pole system with varying phase margins. The plot is normalized in two ways. First, the closed loop gain is normalized to 1 or 0 dB, and second, the x-axis or the frequency axis is also normalized such that the unity gain frequency of the loop gain is placed at 1 radians per second or 10 raised to 0. As shown, different phase margins result in different amounts of peaking in the closed loop response. As the phase margin is reduced or decreased, the peaking approaches infinity as the circuit becomes critically stable. The closed loop gain will have an infinite magnitude at the loop gain unity gain frequency if the closed loop poles lie exactly at the imaginary axis. This is the boundary between being stable and unstable before the poles enter the right half plane of the S-plane. The case with a phase margin of 75.96 degrees is drawn in red. It is the critically damped case with overlapping poles and has a flat response with no peaking. For the green plot, the phase margin is 60 degrees. The normalized closed loop gain at the normalized unity gain frequency is exactly 0 dB. However, there is around 0.2 dB of peaking before the unity gain frequency of the loop gain. Now, note that the two mentioned cases are the recommended phase margins for a fast response, meaning a system is close to the target phase margin if the closed-loop system is flat or has minimal peaking. The maximally flat response is achieved with a phase margin slightly above 60 degrees. There are other ways by which a two-pole system can be analyzed, one of which is by analyzing what we call the pole Q factor. The denominator of a two-pole closed-loop response can be written in the form S squared plus S omega naught over Q plus omega naught squared. By inspection, comparing the last terms, we can identify that omega naught is the square root of omega p1 times omega p2 times 1 plus t naught, and we call this the pole frequency. For a complex conjugate pole, omega naught is the distance from one of the poles to the origin of the S-plane. Meanwhile, by inspection, Q must be equal to omega naught over omega p1 plus omega p2, but using this expression for omega naught, we get that Q, or the pole Q factor, is equal to the square root of omega p1 times omega p2 times 1 plus t naught over omega p1 plus omega p2. A Q that is greater than 0.5 means that the poles are complex conjugate pairs, or we have an underdamped system. In our plot, the distance between the complex conjugate poles real part and the sigma is equal to 0 line is equal to omega naught over 2q. And thus, if the complex conjugate, if the poles are overlapping at the real axis, then the distance is omega naught, and that will only be equal to this expression here if q is equal to 0.5. But beyond that, the poles will be complex conjugate pairs. Also, if you recall, this distance here is also equal to the average of the original pole locations from the open loop. So this distance here is also equal to omega p1 plus omega p2 over 2. And so this form also confirms that if we cancel 2, that q is equal to omega naught over omega p1 times plus omega p2. Using this analysis as well, it can be shown that the maximally flat closed loop response can be achieved when q is equal to 0.707, or when the poles are at 45-degree angles from the real axis. In summary, the step response of an amplifier depends on the pole locations. For an open-loop amplifier, the frequency response is normally limited by a dominant low-frequency pole. The poles and zeros of the open-loop gain near the unity gain frequency greatly affect the stability when configured in closed loop. At closed loop, the poles move depending on the loop gain. Depending on where the poles end up, the response can be overdamped, critically damped, underdamped, or unstable. The phase margin, as measured from the loop gain T of j omega, the peaking, as observed in the closed loop magnitude response, and the ringing, as observed in the time domain step response, are interrelated and can be used to infer approximately the other. A two-pole system will exhibit a critically damped response if the phase margin is 75.96 degrees. A phase margin larger than this means the system is overdamped, And the closed-loop magnitude response will exhibit no peaking. There will also be no ringing in the step response. Meanwhile, a phase margin less than 75.96 degrees but still greater than 0 degrees will exhibit an underdamped response with peaking at the closed-loop magnitude response and with ringing in the step response. A minimum target phase margin of 45 degrees is suggested to avoid instability with minor variations in design, which includes variation in temperature, supply, component values, parameters, which are all possible to change with component tolerance and component degradation in time. If a small amount of ringing is acceptable, then it is suggested to target a phase margin of 60 degrees to 75.96 degrees to achieve the fastest step response. And that's it for this lecture. I hope you learned a lot. In the next lecture, we will look at compensation techniques to move the poles or zeros in an amplifier to ensure stability or achieve the target phase margins. Thank you very much for listening.